Good afternoon. We have started our discussion on vapor compression refrigeration cycle, which is the most common and most widely used refrigeration cycle. Uh, though there are other types of cycles, but their application are limited, and for special purposes those other cycles are used. So, mainly we will have vapor compression cycle and we will concentrate on that. Now, I will just recapitulate quickly what we have done so far. A vapor compression refrigeration cycle, we will have a compressor and along with this, I mean this is the compressor which will be driven by some external agency like electric motor, and then after the compressor the compressed vapor, basically it is refrigerant in the form of vapor, it will go to the condenser. In the condenser it will reject heat. So, this is the condenser, this is compressor, it will reject heat, and then there is an expansion device, this is the expansion device. After that it will go to the evaporator. Evaporator is the component where the cooling effect is produced. So, it will absorb heat, basically it will absorb heat. So, what happens after the expansion device, the pressure of the refrigerant falls and it is at low temperature in the evaporator, and it is also in the liquid condition. In the evaporator it will evaporate and it will absorb heat. So, it will produce cooling effect. At the same time it will get transformed into vapor state, but this vapor, this refrigerant vapor is at a low pressure. So, to continue the cycle it has to go back again to the compressor to be compressed and go to the condenser. So, this is the way the cycle will be executed. So, there are number of variations of this basic cycle, and also I like to once again make the sketch of the thermodynamic diagram of the cycle, and we know that it is better explained with the help of a pH diagram. So, which way we get P and which way we get H? So, this side is your pressure and this side is your enthalpy. This is the two phase dome in the pH plane, and somewhere you have got the critical point. So, this is the expansion process. So, we have started with the expansion process, sorry, the compression process. This is 1, that means it is at the entry of the compressor. Then this is 2, that is at the exit of the compressor. Then it goes all the way to the saturated liquid condition, and in most probable case it is also subcooled slightly, and then we will have some Joule-Thomson expansion process which is irreversible, and we can express it with the help of a dotted line, but most of the cases it is shown by a firm line because we assume that it is along this constant enthalpy path. So, 1, 2, 3 and 4, and here also you will have 1, 2, then 3, then after expansion this is 4. So, basic cycle and basic cycle thermodynamic cycle diagram has been shown here, and this is more or less the ideal diagram of the cycle without assuming any sort of irreversibilities. Of course, this 3 to 4, this process is an irreversible process, but apart from that we have not considered any other losses anywhere. but in actual practice we will have number of deviations from the ideal cycle. So, we can have a small discussion regarding the deviations. What sort of deviations we will have? See, the ideal cycle, of course, if somebody wants to discuss it, that it should start just at the saturated vapor condition. That means, the compression process should start at the saturated vapor condition. But in actual practice, there is little bit of superheating. Okay. What happens after the evaporator? The vapor has to come through the valve and it has to go to the compressor through the valve passages, ports, etc., which are at relatively higher temperature. So, these passages not only they will induce certain amount of pressure drop, but they will also induce certain amount of superheat. Okay. If we assume that the vapor is entering at saturated condition, even if it enters the valve port at saturated condition, as it picks up certain amount of thermal energy, it will get superheated. Okay. So, here of course, it has not been shown, but there will be some amount of additional pressure drop and some amount of superheating. Then 1 to 2, this is a compression process. In ideal case, we assume this compression process to be isentropic, but we will not have isentropic compression process in any of the compressors which we can design or which we can manufacture. It will deviate from the isentropic compression process. It will deviate. There are number of reasons for the irreversibilities, but the main reasons are: 1, we assume isentropic process means reversible adiabatic process, but the process is not adiabatic. There will be some amount of heat transfer. During compression, the vapor will be at high pressure and it will also gain temperature. That means, its temperature will also rise. So, at that time there will be heat transfer and there will be frictional losses. So, the gas when it flows through the compressor, whether it is a positive displacement compressor or it is a rotary compressor. So, in every case there will be friction. So, we will not have adiabatic, reversible adiabatic process in the compressor. All right. So, if somebody wants to go for a detailed calculation of the compression process, so it will not be advisable to take the compression process as an adiabatic compression process. So, one can take it appropriate, one can take appropriate polytropic expansion, compression for the gas inside the compressor. Then after that the gas will come out. Again, when it is coming out, then it has to go through the valve passages, the pipeline, and then it has to go to the condenser. So, here also that means at the exit of the compressor, there also it will have some additional pressure drop, okay, because the valve passages are restricted small passages. So, there we will have additional pressure drop, and obviously it will come out at a high temperature after compression. So, when it is passing through the pipeline connecting the compressor and the condenser, there will be some amount of heat transfer. Generally, this is de-superheating. So, we will have some amount of de-superheating, then it is going to the condenser. The condensation process, we assume it to be constant pressure process. Well, there will be whatever small it may be, there will be some amount of pressure drop, because it has to pass through narrow passages, narrow tubes, etc. So, there will be certain amount of pressure drop, and in ideal case one may think of that the condensation is just stopping when the refrigerant has reached the saturated liquid condition, but in actual practice it may not be possible. So, there will be certain amount of subcooling. So, there will be certain amount of subcooling. So, the subcooled liquid then will go through this expansion process. So, initially when the liquid is entering the expansion device, it may be in the subcooled condition, but then expansion will Joule-Thomson expansion will take place and it will come out as a two phase mixture. Again, in the expansion device, the process is very complex. Whatever expansion device it may be a thermostatic expansion valve or capillary tube, whatever it may be, the process is very complex, because here we can have the flow of a two phase mixture, or we will have a flow of two phase mixture. So, continuously there will be more and more production of vapor phase. Okay. So, you can see that this is starting from almost saturated liquid, but as it goes in the downward direction, as its pressure reduces, then more and more vapor generates. This is some kind of a flashing process. So, we will have more and more generation of vapor, and the obviously the process is more complex and lot of irreversibilities are involved with it. But even then one assumes that here enthalpy remains constant during this process, and one can make some sort of a design of the expansion device. So, then ultimately when it reaches the evaporator pressure, then we will have the evaporation. Again in the evaporation process, we will have pressure drop, whatever small it may be. Though we are assuming it is a constant pressure process, it will not be so. We will have certain amount of pressure drop. So, these are the deviations from your actual vapor compression cycle to the these are the deviation between the ideal vapor compression cycle and the actual vapor compression cycle. Now, certain features of these deviations are desirable from practical point of view, particularly this superheating of the refrigerant vapor after the evaporation process or before its entry to the compressor. It is quite desirable, because we do not want to send any liquid refrigerant into the compressor. That is why sometimes in larger establishment, means in larger refrigeration unit, you will have device which helps the superheating of the vapor after the after it comes out of the evaporator. So, what one can have basically one can have one additional heat exchanger. Are you aware of it? Sometimes this is called suction line heat exchanger, and there is heat exchange between this and this line. Okay. One can have one additional heat exchanger between see the refrigerant after the condenser, and it is before the compressor. There can be one heat exchanger. So, if we try to draw that, it will be something like this. So, we will have condenser, then there is one heat exchanger, then there is expansion device, then it is going to the evaporator. Well, this is the evaporator. After the evaporator, comes to the same heat exchanger, it goes here. Okay. So, okay, let me. So, this is your condenser, this is the expansion device, this is the evaporator, and then we will have heat exchanger. So, after evaporator it is going to the heat exchanger. What we are getting that in the after condenser, when the refrigerant is coming out, still it is having slightly higher temperature. So, this heat can be utilized by the refrigerant which comes out of the evaporator, so that it guarantees that the refrigerant will enter the compressor in the superheated condition. All right. So, this is not there in small system, but large refrigeration systems we will have this type of system, I mean this type of arrangement. Well, now so far so this is for the basic refrigeration principle and basic refrigeration system. What one can have large number of variation of this, and particularly when we have to, let us say we can have we want to create low temperature. So, what one can do, one can use two refrigeration cycle in cascade. Okay. I will not go into details of it, just I will make some sort of verbal description of it. See, one can have two refrigeration cycle in cascade. That means, the heat absorbed by the evaporator of one cycle, or the heat will be absorbed by the evaporator of one cycle from the condenser of other cycle. So, obviously, by this we can create much lower temperature. Okay. That is possible. Then one can have multi pressure system, one can have multi evaporator system. So, these are different variations of the basic refrigeration cycle, and depending on our requirement one can have this type of variations. Okay. Sometimes we want to have the variation to have a higher COP, sometimes we want to have this variation to have a lower temperature. Okay. So, depending on these things, depending on this demand, we will have the variation in the basic refrigeration cycle. But most of the refrigeration cycles, what I have told earlier, they work on the vapor compression principle, and where Joule-Thomson expansion is the basis for the production of cooling effect. Now, there are other type of cycles also, and as I have told, it is vapor compression cycle. One can use other type of refrigerant, like a gas can be used as a refrigerant. So, those are gas refrigeration cycle, they have special usage, and I think for marine system those are not very relevant. So, we will not discuss them. Let me have a small discussion regarding refrigerant. To have a desired cooling effect at a given low temperature, it is very crucial to select the proper type of refrigerant. Now, most commonly used refrigerant till a few years ago, even now in number of large systems, is chlorofluorocarbon or we will have different component different chemicals under this group in this group. So, mainly they are chlorofluorocarbons. Okay. And these refrigerants actually give lot of advantages. So, till date they were being used. Now also they are having, I mean we are having this type of refrigerants in big systems, in domestic systems, also some of the old domestic systems, but it is being phased out because they have produced some depletion in the ozone layer, and now we what we call eco-friendly refrigerant. So, people are trying, just as a few years ago chlorofluorocarbon was the only name. Now, we can see lot of other refrigerants, new refrigerants, which are generally termed as eco-friendly refrigerant. Still we have to see which one is the best. People are trying different refrigerant. Of course, commercial systems are there with different refrigerants, but we have to still find out which one will be the best performer, and probably after a few years we will again, just as R11 or R12 or R22 has become very popular, similar type of thing we will get, but now it is the experimental stage. So, we are trying certain refrigerants, they have got some merits, at the same time they have got certain demerits also. So, we have to watch and see. Now, only one thing I like to mention this, as the chlorofluorocarbons are quite common, they can be expressed with a common formula CmHnFp Cl(q). This could be the general formula of a refrigerant, which are most commonly used. CmHnFp, this is carbon, then hydrogen, then fluorine, then chlorine, and these are the number of molecules which are having in this particular component. And then if we have this formula N plus P plus Q, N plus P plus Q is equal to 2m plus 2, then from here one can calculate the value of m. These are known quantities m, n, f, q. So, and from there one can have the name of the refrigerant as R, m minus 1, n plus 1 and p. This is the name of the refrigerant. So, generally the refrigerant name is expressed as R, and then there are 3 numbers, sometimes 2 numbers, sometimes 3 numbers. So, these 3 numbers comes from this particular formula. All right. We can take one example like CCl3F. Can you tell me what will be the name in terms of R? So, this will be R11. Let us not waste time, you can see it. So, this will be R11. Okay. Similarly, we can get the name of other refrigerant, or generally commercial name, or most commonly used name is this. From here we can find out the chemical formula. That is why I have given this. Now, it is needless to elaborate the discussion, but we know that the refrigerant should have certain properties, so that one material will be selected as refrigerant, and depending on application we will find that we have got a very wide range of refrigerants. Okay. That some of the permanent gases like sulfur dioxide, like carbon dioxide, even carbon dioxide nowadays is again being tried. Long back carbon dioxide people used to have it as refrigerant, then with the discovery of the chlorofluorocarbons, different chlorofluorocarbons, this has been abolished or abandoned, but now again carbon dioxide is gaining importance. So, carbon dioxide, sulfur dioxide, ammonia, etc., they are used as refrigerant, even water can be used as refrigerant, air can be used as a refrigerant, but they have got different ranges of operation. So, there should be some properties for this refrigerant, like what properties are important for one refrigerant to perform well, which are the properties one should look for. Well, specific heat is one thing, but before that one has to see that what is the pressure temperature relationship for boiling and condensation. Okay. Let us say evaporator. What we want in an evaporator? An evaporator should extract heat, but let us say extract heat at a low temperature. The evaporator should extract heat, or the refrigerant should be such that it will extract heat in the evaporator at a low temperature. Let us say to create that low temperature, we have to have excessively low pressure. Then what will be the disadvantage?
Very high pressure difference will be required.
That is one thing, and we have to maintain a high vacuum. Okay. We have to maintain a very high vacuum. We have to handle very large volume. Okay. And if it is having excessively high pressure, then what will happen? Then the design of the, I mean all the section has to be made very thick. So, these are the problems. The critical point should be high enough for a refrigerant. Then there are other things, it should be compatible with metal. Generally the refrigerants are closed system. Okay. So, they should remain there inside this closed system for years together. So, okay. So, without having any sort of chemical deterioration or reaction with the metal. Then they should be cheap, they should not be toxic, because if there is any leakage etc. And over and above, nowadays this environmental issue has come that they should be environment friendly. So, that is how the refrigerants were selected. Before the environment issue, before people become aware of this ozone depletion, we were very happy with our this chlorofluorocarbon groups, but nowadays we have to try something else. So, that is all. I what we will do, we will take up problems on this basic refrigeration cycle, and if time permits, I like to take up, of course, that is afterwards, some vapor absorption refrigeration also. I do not know how far it is important in case of marine system. Marine system, you have vapor absorption? No, then I will not discuss it. So, we will mainly concentrate then on problems on vapor compression cycle, and we will spend some more time on air conditioning system. Okay. Regarding the system details, I think it is needless to discuss more. We do not have much variation in marine system, whatever I have seen from different books of this one. So, basically there will be these 4 components, and in some bigger system we will have that internal heat exchanger. So, these are the thing we will have, and there of course, those refrigeration systems are large. So, we will have thermostatic expansion valve there, and mainly the evaporator and condensers, they are cell and tube heat exchangers, and compressors, they are reciprocating compressor, or in certain cases they are centrifugal compressors or screw compressors are also there. So, this is basic configuration of any marine refrigeration system, otherwise there is no such speciality, and we will take up some problem to see the numerics. Well, now what we like to do is we go for the application of refrigeration. Now, refrigeration has got different applications. One of the main application of refrigeration is air conditioning. Now, air conditioning, as the name suggests, it is conditioning of air. It is not merely cooling of air, but conditioning of air. We will come into this aspect afterwards, but why refrigeration and air conditioning all are, I mean, these two words are uttered almost in one breath, because they are very closely related, and a main function or a main activity in air conditioning is cooling the air, and that is not an easy job. We will discuss it also afterwards, that we will see that cooling of any object is rather difficult proposition compared to heating it. Okay. Because I mean, one can easily have some heat source, either from firing fuel or burning fuel or by electrical heating, and heating can be done, but for to have cooling or to extract heat, one should have some elaborate arrangement. And we can see that one arrangement could be air conditioning or vapor compression refrigeration or vapor compression refrigeration. But as in air conditioning, we have to deal with the conditioning of air, which generally deals with these functions: heating of air, then cooling of air, humidification of air, dehumidification of air. So, before going to the systems and processes of air conditioning, we have to study little bit the properties of air, or particularly properties of moist air. Now, you see, in air conditioning, these are the four basic functions generally we do. There are other functions also, that heating of air, cooling of air, humidification of air, and dehumidification of air. And in most of the cases, we will see that we have to do these operations simultaneously. Means, probably we have to heat and humidify the air, cool and dehumidify the air. So, we have to have these operations simultaneously. Humidification and dehumidification means that, well, we have to control, or in other words, we have to control the amount of water vapor or moisture in the air. So, sometimes we have to extract certain amount of moisture from the air, sometimes we have to add certain more moisture to the air. So, basically the medium of air conditioning by which we will create the comfort condition, that is moist air. So, moist air, and we will study the property of moist air. So, properties of moist air, it has got a special name, psychrometry. We have got a special name for this branch of science, we call it psychrometry. Now, in this, basically we deal with a gaseous substance. This gaseous substance is made up of two things. It is dry air, and this is water vapor. And if we combine these two, we will have moist air. Let us say dry air has a mass of m A. Water vapor has a mass of m V. So, moist air will have a mass m, which is equal to m A plus m V. Okay. And this will have, let us say this is having a volume V A, this is having a volume V V. So, it will have a volume V is equal to V A plus V V. Now, what is important that water vapor as well as dry air both are in gaseous state and at low pressure both behave like ideal gas. Okay. And our air conditioning application, for our air conditioning application, pressure range, what is the pressure range? Atmospheric air, atmospheric pressure, slightly above or below atmospheric pressure, not exactly atmospheric pressure, sometimes it will be slightly above or below atmospheric pressure. So, we can see that our pressure range is low pressure range only. Okay. And at that condition, both dry air and water vapor, they behave like ideal gas. So, basically moist air we can take it as a mixture of two ideal gases, and that is how our analysis will be based on. So, we will have the analysis based on a mixture of ideal gases. Only one thing one has to remember in this analysis, what we will do, this dry air we will call fixed component. Let us say, let us take a sample of moist air. In that certain amount of dry air is there, certain amount of moisture or water vapor is there. The mass of the dry air will not change. Okay. So, we will take it as the fixed component, whereas the mass of the water vapor, we can have more water evaporated into that sample or certain amount of water vapor precipitated or got condensed. So, we will have this as variable component, NT, sorry. So, this is the fixed component, this is the variable component. Now, why we have made a demarcation like this, what is the advantage? All the properties we will try to express in terms of the fixed component. See, in other application or earlier what we have done, properties sometimes we have expressed per unit mass. Here we will express it per unit mass of the dry air. Okay. So, not the total mass, but per unit mass of the dry air. So, then the scenario is clear in our in front of our eyes, that we have sample of moist air which will constitute of dry air, certain amount of dry air and certain amount of moisture or water vapor. Okay. The dry air content that will remain fixed, but the moisture content that may vary. Okay. And this mixture will obey the law of ideal gas mixture. So, Dalton's law of partial pressure and other laws it will obey. First, we will try to define certain properties of moist air. Some definitions. Specific humidity humidity ratio. In certain books, this is also called the absolute humidity, though the specific humidity is more common name or more commonly used name. This is expressed by a symbol. Conventionally, this is expressed by a symbol small w, and it is mv, mass of water vapor, divided by ma, mass of dry air. So, we can write mass of water vapor by mass of dry air. This is your specific humidity or humidity ratio. Then mv one can write as V by Vv, where Vv is the specific volume and V is the total volume. Then one can write Ma is equal to V by Va. So, omega or small w, that is Va by Vv. This is what we can write. Then again one can write P A V A is equal to R by M A T, where R is the universal gas constant. P A is the partial pressure of dry air. P A is the partial pressure of dry air. V A is the specific volume of dry air. And one can again write P V V V is equal to R by M V to T. All right. For a particular sample of moist air, one can write it. Then one can write P A into V, that is equal to M A R by M A T, and P V into V, that is equal to M V R by M V to T. What are these capital M A and capital M V? These are molecular weight of the dry air and water vapor. Again here you see, dry air is a mixture of different gases, but as a whole we are taking these to be an ideal gas. Okay. See, dry air basically it is not a single component, there are number of constituents, but we are taking it as an ideal gas, and water vapor is another ideal gas. All right. Should we move on? Well, then we can write omega is mv by ma and pv by pa, and then we can write, putting these values, 18.016, this is the molecular weight of water, and then we can have 28.966, 29 actually, or approximately, this is the molecular weight of air. So, we will have 0.622 PV by PA. all right. So, what we have got? We have got the specific humidity in terms of partial pressure of water vapor and dry air. We can have slight modification in this equation or simplification in this equation. We can write it like 0.622 PV vapor pressure of this is vapor pressure or partial pressure of water vapor, and this in case of instead of PA we can write P the pressure of the mixture minus PV, because from the law of partial pressure we know PA plus PV. So, that is what I have used here, and generally the water vapor amount of water vapor is very small in a mixture. So, its partial pressure will also be small. Okay. So, now we can use this symbol 0.622 PV by P. So, you see by some simple measurements we can determine what is the specific humidity or humidity ratio. What we have to do? Suppose now in this room we want to know what is the specific humidity or humidity ratio. We have to know the pressure, all right. We have to know the vapor pressure, okay. We have to know the total pressure that can be measured with the help of a barometer or something like that. We have to know the vapor pressure, okay. And then using this PV and P, then using this formula we can determine what is the absolute humidity or specific humidity. So, generally what happens, we have got chart depending on temperature what is the vapor pressure that can be obtained, and from there also one can calculate what is the specific humidity, all right. So, basically in this connection we like to tell one thing, that as I have told, properties of moist air are expressed in terms of unit mass of dry air, all right. So, basically what we do for the sample, if we want to do the express the properties, then it is basically for 1 kg of dry air. Then what will be the weight of the sample? Weight of the sample will be then mass of the sample of moist air will be 1 plus this much kg. Okay. What is W then? W or omega? Small w or omega? Small w or omega is the mass of water vapor for 1 kg of dry air. So, what will be the unit of omega? Unit of omega?
So, there is no, it is a relative.
Yeah. So, kg per kg dry air, kg per kg dry air. Now, if we express it kg in kg per kg of dry air, then the number becomes very small. So, sometimes it is expressed grams per kg of dry air. Okay. So, grams of water vapor per kg of dry air. So, this is kg per kg of dry air. So, let us stop here and take a small break, then again we will start.